Okay, I've got two billiard balls, and I'm going to change the zoom of this camera just a little bit and re-aim it. And I got to zoom back a little to get everything now. I should have stayed where I was maybe, but there we go. Okay. Now, I've got two billiard balls. Now, if these are rolling along a table, and let's assume the table is frictionless, which isn't the case in any real situation, but if the balls approach each other, they could hit head on and bounce off like this. Or they could hit a little off center, and then they bounce like this. Okay. We want to draw a picture of the two billiard balls in a general collision. Okay, so, well, let's just say they're both moving along the horizontal direction. Well, maybe they aren't moving along the horizontal direction. But let's say that we just decide that we're going to put the two balls in a horizontal configuration where the line between the centers of the balls is horizontal. Okay? Because that's what most people did when I asked them to draw a picture of the forces. And that's okay, you can do that. In this case, what's the nature of the forces when the balls are in contact? Okay? When the balls are in contact, what's the nature? Well, you know what really happens, and you can imagine these are softer rubber balls. They come together here. Now if I try to force them together, it's going to compress them. It's actually compressing these pool balls as well, but it's a little hard to see how much it compresses because it's only, you know, down in the microns someplace. Very small because these things are very hard. Okay, but they're also very elastic, meaning that you compress them and you do a little bit of work, and when they come back apart, they most of the energy that went into compression comes back in the form of kinetic energy. Okay, so they hit like this. The force they exert on one another is, each of those forces is a normal force. It comes about from compressing one of the balls, and it then wants to decompress and exerts a force on the other ball. There's a more specific way to talk about those forces, but intuitively that works, and that's pretty much all we need right now. Okay, so the result of that is, well, the contact forces are normal forces perpendicular to the tangent line. What tangent line? The tangent line at the point where the balls meet, the common tangent to both of the spheres. Of course, you know, we're assuming the spheres don't compress much, so we really do have a tangent line at a single point. Okay, so in that case, well, again, the forces have to be perpendicular to the tangent line. That's just the way the balls compress and decompress. Well, this forms what we call an action-reaction pair. And the action-reaction pair gives you equal and opposite forces by Newton's third law. Okay, that's an action-reaction pair of forces. The forces are equal and opposite by Newton's third law. So the two forces that I've depicted here, F12, the force exerted by ball 1 on ball 2, and F21, the force exerted by ball 2 on ball 1, are equal and opposite. I can't quite read the 1 on that subscript, but there it is. Okay? Now, by all this, these forces are equal and opposite, and they're also exerted along the line joining the center of the two balls. So the line through the common center. Okay, so that's the nature of the forces. Now we'll go on and take account of the direction of one or more of the balls prior to collision.